So students, welcome back to another session of mine. In today's video, we're going to be continuing our calculus series. I don't know what about this video is. I mean, you guys probably will get to know by the time I upload this one, because I will obviously have it written down in the title itself. In the previous video, I believe I introduced you guys to integration, but since that video was being way too long, so I just did not have the time to introduce two very important topics. First one is the integration constant. Like I mentioned to you that when you integrate 2x dx, you get x square, but that is not totally true. When you integrate 2x dx, you get x square plus the constant c. I totally forgot to mention about that, and I'll definitely explain it to you guys. This one. Another important topic I forgot to mention. I totally forgot to mention about it actually. Or did I? I'm getting lost. It was about limits. Limits of an integral. Or to be more specific, in terms of integration, we call it bounds. Lower bounds and upper bounds. It to be p of 2x is gonna be p square minus a square. So let me try to explain it. This topic to you guys today. First of all, the integration constant. Whenever we integrate a function, let's say a function called 1 upon x dx. Whenever we integrate this function, I definitely taught you guys how to integrate this function. This integration would give us ln of x. So this is partially true. Why? Because you would have a constant. Now you might ask, why am I gonna put a constant at the end of this integral? The reason behind that is this function that we are gonna be integrating here is nothing but the derivative of the function that we get after integrating this original function 1 over x, which in this case is 1 over x. So if you differentiate ln of x, you get 1 over x. But when you differentiate ln of x plus some constant, let's say c, this becomes derivatives of ln of x plus derivatives of some constant c. And you must know that any constant when you derive it and you differentiate it, it becomes 0. Why it becomes 0, you must ask? Because it's a constant, and derivatives tells us nothing but the rate of change of that function. And since this is a constant, so this just would not change. So its rate of change would be 0, right? So the resultant derivative of this function over here, ln of x plus some kind of constant c, would also be 1 over x. So then that means we can have a lot of different possibilities of ln of x added or subtracted to some kind of constant, and whenever we differentiate it, you would get 1 over x. So that means 1 over x when we integrate this integration with respect to dx just wouldn't give us one answer. It would give an answer which includes this natural log plus a constant which counts for limitless other possibilities. The same can be said for other functions. Let's say I have a function here of 3x dx. Okay, this would result in you would have to increase the power of x by 1, and it's already power already is 1. Let's multiply by 3, and uh, actually a better way to do it would be to take 3x square here. So 3x, this will be 2 plus 1, x to the 2 plus 1 over 2 plus 1. This would be 3. This would be 3 times x cube over 3, and this through 3, just 2 3's would cancel each other, and this would just leave us with x cube. But that is wrong. That is partially true, because we're again forgetting constant here. Because whenever you differentiate this function, x cube plus some constant, you would get 3x cube. So this means there are also limitless possibilities where you're integrating this function 3x square with respect to dx, and the result of that, there might be infinite number of possibilities of that. So this constant counts for every single possibility of that. If this constant is 0, then integrating 3x square with respect to dx will just give us x cubed. So this is why whenever you integrate a function, you would need to add a constant at the end. Understood? I think that can be the best possible explanation I can give regarding this topic. Okay. Another topic was about definite integrals with bounds, upper and lower bounds. Let's say we have a graph here. Let's say a function f of x equals x square. The graph of this function, the x-axis represents the value of x, and y-axis represents the value of f of x. This graph would look like something like this, and we have two points in this graph, A and B. So let's assume that we encounter a mathematical problem where you would have to find out this particular area, the area between points A and point B. How would you do that? How someone would logically approach this problem? What do you guys think? I don't know about you guys, but like the mathematicians who create integration says that we would need to at first find out the total area under this curve from point 0 to point B, that is this total area, and then you would have to find the area under the curve from point 0 to point A. Then when you subtract the smaller area, that is from point 0 to point A, from the bigger area, that is from point 0 to point B, you would get this area. You basically what you're saying that you would take this area at first, then you would take this area, then you would from this one we're gonna subtract this one, so we would end up with this one. So this is how this thing is gonna work. If you want to find this this area under this between 2 points on this curve, between 2 points, we write it down this way: f of x dx, and on the bottom of the integral sign we write a, and top of this we write b. This represents the lower limit or the lower bound of the function, and this represents upper limit of the upper bound of the function. And when you would integrate this, you would since you know f of x is x square, so when you integrate that, you would get it would be x cube over 3 plus a constant c. But since this is what is this? This is just sorry about that. This is just a general form of how this area and this other total area under this curve would look like. But we are forgetting that, I mean, we have been asked to find this particular area, the area under this graph from point A to point B. How do we represent that? Again, at the bottom right corner we write down A, and the top right corner we write down B. And then we have to substitute B for X. You get b cubed minus 3 minus b cubed by 3 minus a cubed by 3 and plus our constant. Now this is how this thing works mathematically, but you can also logically visualize this. So we have been asked to find out this area under this curve from point A to point B. Okay, so what is this area from under this curve from point 0 to point B? And the general form of the area under the curve is x cubed over 3. That is the corresponding value of x at that point. That thing cube, that whole thing divided by 3. At point B, the value of x is b. So when we substitute b into this function, x cubed by 3, you would get b cubed by 3, and this b cubed by 3 is this total area under this curve from point 0 to point B. And the same thing when we do it point A, you look at this total area, that is from point 0 to point A, the area under this curve from point 0 to point A. And here we are subtracting the area from point B, from 0 to point B, and from it we are subtracting the area between point 0 and point A, and that would give us this area plus our constant, of course. So I think this should be a pretty good explanation of what is going on here. So this was today's video. In today's video I talked about two very important topics. Why do we have to add a constant at the end of an integral, and what is a definite integral? Oh, actually, this is a definite integral because the upper and lower bounds, those are defined. We know what those are, a and b. In this case, it is a and b. And for integrals of which we have not been told what the upper and lower bounds are, and we just have to figure out what the general form of the area under the curve looks like. That kind of integral is called an indefinite integral, like this one over here. In this one, we have just been asked to, let's say if we have not been provided with the bounds, upper and lower bounds, then we would have just calculated how this general function describing the area on this curve would look like. That would be x cubed by 3. In this integral, then this integral would have been an indefinite integral. But since this one has provided the upper and lower bounds of the area that we have been asked to find out, this one is a definite integral. So I think that should be enough for you guys to comprehend all this. If you guys think that if I missed any important point, then definitely do let me know in the comments. And if you think you still have yet to understand regarding this topic and you are still a bit confused about what is going on here, you can definitely let me know about that in the comments. So that is for today, guys. See you tomorrow and keep learning.